4.3, and it's on solution chemistry. And we're going to look at the composition of solutions and focus on molarity. So you probably remember that molarity is moles of solute over liters of solution, and our equation is M equals N over V. M representing molarity, N number of moles, and V for volume, which needs to be in liters. When you make a molar solution, it needs to be in a volumetric flask. So in this illustration, we see a lot of various sizes from 500 mils, 1,000 mils, 250, 100. You'll be using those eventually. So to make a molar solution, you can take your solid, place it in your volumetric flask, and then add deionized water, or distilled water, fill it up partway, dissolve your solid, and then, shaking periodically, fill it up to the mark. And that mark represents 1 liter of solution of whatever concentration you've been making. So our first calculation is calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1 liter of solution. So remember, our equation is M equals moles over volume. So I need to take my mass of sodium hydroxide and change it to moles, because that's my solute. So 11.5 grams of NaOH. We have 1 mole of sodium hydroxide in the numerator. The molar mass of sodium hydroxide, 1N, 1O, 1H, is 39.998 grams. And here we see our grams cancel, and we have moles of NaOH, and keeping a little bit of extra sig figs, you can just keep it in your calculator. But we have about 0.288 moles of NaOH. To calculate the molarity, I'm going to take my number of moles, 0.2875 moles of sodium hydroxide, and put it over the volume of solution in liters. So I have 1.50 liters of solution. When you divide through, you have a solution that has a concentration of 0.192 molar NaOH. Let's look at another one. This time, let's calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous HCl in enough water to make 26.8 mils of solution. So we're going to take the hydrogen chloride as a gas and change it to moles. So that's our first step. Our second step will be to change our milliliters to liters and then calculate the molarity. So starting with 1.56 grams of HCl times 1 mole of HCl over 36, here we are, 0.958 grams of HCl. So just the molar mass. It's a small amount. We should have a small number of moles. It's 0.04279. Again, just add a couple of extra sig figs if you are truly writing it down, or keep it in your calculator. Now, our moles is that 0.04279 moles of HCl. We're going to change our milliliters to liters. So dividing by 1,000, we have 0.0268 liters of solution. Divide it into our moles, and our concentration is 1.596, which will round to, we just want 3 sig figs, 1.60 molar HCl, or hydrochloric acid. Our next example asks for the concentration of each type of ion in the following solutions. So remember, cobalt nitrate will dissociate into its ions, which means it forms 1 ion of cobalt plus 2 ions of nitrate. Now, if I have a 0.5 molar solution, you can use the mole ratio to determine the concentration of the ions. So your cobalt is 0.50 molar, and our concentration of nitrate is just 2 times the 0.5 molar, so we have 1.0 molar concentration of nitrate. Let's look at the iron 3 chlorate. When it dissociates, it's going to dissociate into the iron cation and 3 chlorate ions, each with a -1 charge. If we have a 1 molar solution, in solution you will have 1 molar concentration of iron 3 and 3 molar concentration of the perchlorate ion. Let's calculate the number of moles of chloride ions in 1.75 times 1.75 liters of a 1 times 10 to the -3rd molar zinc chloride solution. So, we want the chloride ions. First thing I'm going to find out will be the number of moles of zinc chloride, so M times V. So, my molarity is 1.0 times 10 to the -3 molar, and my volume is 1.75 liters. So I have a concentration of zinc chloride of 0.00175 moles. Now zinc chloride, when it goes into solution, it dissociates into zinc ions and chloride ions. And we have 2 chlorides for every zinc. So our ratio for zinc chloride, or for the chloride ions, will be 2 times the concentration of our zinc chloride, 0.00175 moles, which will give us 0.0035, I'm going to round to 2 sig-figs, moles of chloride ions. Another one, like some small amounts, it says typical blood serum is about 0.14 molar NaCl. What volume of blood contains 1 milligram of NaCl? So we want volume. We know that moles over molarity will give us volume. So my first step is to change my milligrams to moles. So 1 milligram is equivalent to 1 times 10 to the -3rd grams of NaCl. And now we'll change it to moles. 1 mole of NaCl has a molar mass of 58.44 grams. And we have a small amount. I changed it to scientific notation, 1.71 times 10 to the -5th moles of NaCl. Now we want to know how much blood. So our volume is equal to the number of moles, 1.71 times 10 to the -5th moles of NaCl, divided by the molarity, 0.14 molar. That will give us liters. If you think about molarity as moles over liters, the moles will cancel. Your liters is in the denominator of the denominator, and it gives us 1.2 times 10 to the -4 liters. If I multiply by 1,000, I get 1.2 times 10 to the -1 milliliters. Or you might like 0.12 mils. Now, a standard solution is one whose concentration is accurately known, so it's made very precisely. So let's say they use potassium dichromate to analyze alcohol content. So it says to analyze the alcohol content of a certain wine, a chemist needs a liter of an aqueous 0.2 molar potassium dichromate solution. How much solid potassium dichromate dichromate must be weighed out to make this solution. So first step is to take molarity times volume to get how many moles we need. So kind of an easy one here. 0.2 molar times 1 liter, we need 0.2 moles of potassium dichromate, K2Cr2O7. So our next step is just to change it to grams. So 0.2 moles K2Cr2O7 has a very large molar mass. Oops, let me put it in the right spot. 1 mole of K2Cr2O7 has a molar mass of 294.2 grams. K2Cr2O7 multiply through, and we are going to mass 58.8 grams of the substance to make a point. Oops. Let me write it and then I'll talk. K2Cr2O7. You're going to mass 58.8 grams of potassium dichromate to make 1 liter of a 0.2 molar solution. So sometimes we take those stock solutions and we use it to dilute it to make other solutions. So I buy concentrated acid. Hydrochloric is usually 12 molar that I purchase, and you use that to dilute. So dilution, moles of solute after the dilution is equal to the moles of solute before the dilution. So we can look at, if we had before, we'll call that 1, M1V1 equals N, and then after the solution, you have M2V2. It too equals N, so we can drop in and use a new formula, which I'll show you in a second. To dilute, we use a pipette, and we measure very precisely. So it's a graduated or more pipette that has the graduations. The volumetric only measures 1 value. Our procedure is you transfer the solution, the stock solution, to a volumetric flask. You usually want some deionized water in it first because whatever you're transferring is more concentrated. And then you add water to the mark and you have your dilute solution. So the representation, notice there's some deionized water in the volumetric flask. They add the concentrated and now fill water up to the mark. And now you have your new concentration. So here's that equation I was looking for. M1V1 equals M2V2. And let's work that equation, problem. A volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.1 molar sulfuric acid solution. So I'm going to use 16 as my M1, and I'm going to find V1, how much of that I need to make my 0.1 molar solution, and I need 1.5 liters of it. Solve for V1, pretty simple. And you have a very small number because that's in liters, so 0.0094 liters. Change it to milliliters, and you'll know that you need to add 9.5 milliliters of the concentrated acid in a 1.5 liter flask to prepare a 0.1 molar solution.